Okay, here we go. Classwork 3.3. You are going to learn the first log rule that you are ever going to learn. And here it goes. We start with exponent rules. You already know exponent rules. So if you have b to the power of m multiplied by b to the power of n, what is the exponent rule that condenses that into one exponential? What do you do to the exponents? You add them. And as a quick example, let's say this was b squared times b cubed. Just get a nice picture look at this to realize that that means you are multiplying 2 b's and you're multiplying 3 more b's. So you are adding the number of b's that are multiplying. Now, what you need to notice is there is an operation that is bonding two separate exponentials outside of them. What is that operation that is bonding those two exponentials? Multiplication. So very important. Notice that multiplication is bonding two exponentials outside of them. Now, what operation is going on inside of the one exponential that happens to be the same thing as? Addition. Now, what do inverse functions actually do? They turn what's inside outside and what's outside inside. Oh, look at all those balloons. Someone had a birthday, I think. Sorry, I got distracted. Moving back. X and Y, yes, X and Y are swapped, and that swaps inside and outside. So inverse functions swap X and Y. And that means that one functions, and let me remember what exactly I had written there. That this means that one function's input inside the function swaps with its inverse function's output outside the function. And I want you to remember this as I show you this log rule, because people remember their log rules often incorrectly, and they do that because they purely memorize. You need to try your best to not just memorize this rule, but I want you to see the connection that I am about to show you with the exponent rule that you already know. I'm going to try to make this screen a bit bigger to be able to show you as much as possible. There we go. All right. Now, right here, again, I have two separate exponentials that are being bonded by multiplication. The log rule bonds two separate logarithms by addition, which is what I have inside with the exponent rules. So that means that if I have log base b of some input x, and I add that to log base b of some input y, that will condense into a single logarithm. And I want to remind you that logarithms are exponents. So if you remember that logarithms are exponents, look at, let me actually do this. Look right here, you have an exponent plus another exponent. You know that you add exponents together when you have two separate exponentials multiplying. So take a wild guess as to what's going to happen inside when I do this reversal. Yes. multiplication is going to happen inside. Now, the notation note that I have is you need to know that I don't have to have a parentheses around the x times y. You need to be aware that it means the same thing if I write it this way. This means x and y multiply, and then that goes into the log function that is base b. However, I feel like they really should have included parentheses with their notation. But know that if you see it this way, well, so it is. So that log rule, you are going to live it, love it, own it, be it, feel it. Today is your day for this log rule. I'm giving you no other log rules today. You must spend time getting to know this log rule. Now, expanding. You need to expand and condense logarithms, and there are reasons why you would want to do that. You're not going to see that at this point in time. Right now, you're just doing the math. So I want you to see with number 1 that you have multiplication inside a logarithm. The log rule we just learned says I can expand that into 2 logarithms with the same base, but separate the 8 and the x that are multiplying, and those logarithms are adding. Number 2. Number 2 looks like it's the same thing, but I'm going to warn you and also tell you that I feel like this is maybe going a little bit too far. For number 2, you are expected to first see that you are multiplying 9 and x together. That means you are adding 2 separate logarithms with that same base that have the 9 separately from the x. If you look at log base 3 of 9, do you realize that that can simplify? Just take a moment, look at it, think about it. 9 is 3 to what power? 9 is 3 to what power? 2. So this actually simplifies all the way down to this. I'm not going to push this on you on tests. It's going to show up in some of your homeworks, but know that I'm not going to push it this far during a test or a quiz. And to make sure that you see that, I'm going to rewrite log base 3 of 9 is the same thing as log base 3 of 3 squared. And I'm going to overemphasize that these are the insides of the logarithm. You want to understand inverses and understand that inverses say if 2 goes into an exponential function with base 3, and that result goes into the exact inverse of that exponential function, which is log base 3, that I will get out what I originally started with, because inverse functions undo each other. When doing log rules, do the base numbers need to be the same? And yes, the base numbers have to be the same in order to add them together. And I'm not going to throw at you anything beyond that in this class. I don't think you really need to deal with that ever. With the technology we have, you don't need to go into some of the crazy stuff that maybe your parents or grandparents had to go into, because technology wouldn't solve it for them. Anyway, number 3. With number 3, we're going to start off with, there are 4 things multiplying there. And if you want, you can just expand this in one swoopy doopy. So I can make this log base 2 of 8 plus log base 2 of A plus log base 2 of B plus log base 2 of C. So I can just expand that quickly. Now, do you recognize log base 2 of 8? Sorry, colorblind people. Yes, log base 2 of 8 is 3. So I'm going to write over to the side here just in case you don't see it. Log base 2 of 8 is log base 2 of 2 cubed. And that means good old plain 3. So the final answer of this being as simplified as possible with expansion is as follows. Know that the bases of your logarithms must always be positive numbers and never the number 1. All right, moving on to number 4. I am going to take 3 things multiplying and separate them into 3 logarithms that are adding. Now, log base 36 of 1/6 can be simplified. Again, I'm not going to push this on you in the middle of expanding on a test. But I will push on you things like, hey, what's that simplify to as an entire problem on its own? So log base 36 of 1/6. What is that actually asking? That is asking what is the exponent on a base of 36, putting a question mark for that exponent, so that I can get an answer out of it that is 1/6. And this is really a bit painful. First of all, you can write this at 36 is 1 divided by 36 to the negative 1 power because of my negative exponent rules. And then do you also see that 6 is the square root of 36? And a square root is an exponent of 1/2. So 36 is 6 to the 1/2 power. In the denominator, it is wait, hold on. Am I messing myself up? Basically, what you need to see is that the exponent you need is negative 1/2. So negative 1/2 plus log base 36 of w plus log base 36 of z. I definitely consider this to be a very big challenge of figuring out that this exponent needs to be negative 1/2. Okay, condensing time. And then we'll be done with logarithms for the day as far as classwork 3.3. So when you condense, do you see how to condense this in one swoop? You are adding logarithms that have the exact same base. Can you do that in one step? Bam. I'm looking in chat. Yeah. There, I'm looking in chat. I'm having trouble reading that. Okay. So what you're saying is log base 6 and then 5QR multiplying together. It doesn't have to have a parentheses around the 5QR, but know that that is what is meant. Okay, 6. I've got to deal with this issue right here, but luckily we saw these loners pop out these lower numbers pop out of expanding. So what you need to do is the other two logarithms that are adding are base 8. You need to rewrite this as a logarithm with base 8. So log base 8 of something is equal to 2. I will answer how do you type subscripts in just a second. It depends on what program you're working. So I want to give you a moment to see if you can figure this out. Okay. So log base 8 of what will give me an answer of 2. If you think about this, it's going to help you for today's quiz. Log base 8 of what will give me 2? Ah, I saw the correct answer show up. Remember that the answer to your logarithm is an exponent. So what it's really asking is, what is 8 squared? And that is 64. Now at this point, I'm ready to condense. So this will condense into one logarithm, base 8. It's going to be 64 times 2t. I'm going to go ahead and multiply. 64 times 2 is going to give me 128, and then times that t and times p. I can choose to leave no parentheses or put a parentheses. It means the same either way. Okay, then that's logarithms. The one thing that I want you to deal with today on logarithms is just know that rule really, really well. Yes. Then divide it by 2. Going this way, you mean? That's when I said that I'm not going to throw this at you in a test. That's why. Because when you're in the middle of expanding something, it is a lot harder to recognize that there's further to simplify. And I don't feel that that is a very fair test problem. Maybe for an honors class, but that's just going a little bit too far. So in homework, you're going to see these like with 2, 3, and 4. But on a test, I am not going to expect you to go that far. In fact, in the homework, I believe I even put the answers down as like, here is good enough, but here is more simplified. So just know that in this class, when you're taking a test or even doing homework, I consider it good enough if you can just use the rule and get to these points that I'm circling. If you're able to see further, that is like bonus. You're seeing more than what I'm expecting. I want you to see what I circled in red. That's important. Okay, so it's time to say goodbye to logarithms for a little bit. And I decided to hold back on this graph. Anyway, I'm throwing into this log unit a couple of other graphs, and maybe it will help you to feel more comfortable with the test when it comes around too, to have some non-logarithm problems thrown in there. So what we're going to do is make a table for y equals x cubed. Some of you, do any of you know what this graph looks like already without seeing it ahead of time? Maybe? Okay. So if I multiply -3 by itself 3 times, I get -27. Agree? Okay, that's fine. You can do the classwork during third period and the homework during fourth period. Negative 2 to the third power will give me negative 8. Negative 1 to the third power will give me negative 1. 0 cubed, 1 cubed, 2 cubed, and 3 cubed. I'm going over this a little bit faster than I would in the classroom because they shorted us a half hour. Now I'm going to plot the points that I can plot. I can plot the point negative 2, negative 8, but negative 3, negative 27 is way out of that ballpark. Then I can plot the point negative 1, negative 1, 0, 0, 1, 1, 2, 8, and then the last one there is also out of the ballpark. Here's what I want you to know about x cubed. X cubed actually flattens in the center. So what I'm going to do is kind of draw a little bit of a horizontal line. Now, the graph technically is not having a horizontal line there, but I'm trying to do this to get you to see that it flattens. It's curvy. It doesn't stop being curvy. It does not actually stay 0 for any period of time. But it goes wha-bam, if I can draw. I want you to see that that curve flattens down there. Wha-bam. I've got a Desmos version of the graph since I knew that there might be a problem with me being able to draw. Where did I put my Desmos? Oh, I put my Desmos over there. I'm going to grab you, my little Desmos friend. And so I have here a nice little visual of y equals x cubed with a table, and take a nice little look at this. And I'm going to close this so that you can see more clearly. Do you see how it is pretty darn flat right there in the middle? It doesn't stay on the x-axis any longer than a single point, but you should be aware that it is quite flat in there, sandwiched a bit. So that is the graph of y equals x cubed. When you graph it, I expect you to always plot a minimum of 3 points. The parent graph has well-known points of negative 1, negative 1, if I can get there. There you go. Negative 1, negative 1, 0, 0, and also well-known positive 1, positive 1. Always start your parent graph with those 3 points. Then do whatever manipulation is asked of you. So I'm going to come back here and we are going to wrap up the classwork with a few more things. The domain and range of x cubed is all real numbers. Negative infinity to positive infinity. Now the inflection point is 0, 0 before you do any movement. If you move your graph, exactly how you move it is going to tell you that inflection point because it is at the center of this graph. And it's an inflection point because if you take a good look at it, maybe I should show you the Desmos version, not my version. There it is. Do you see that over here on where I'm at? This looks like a sad face, doesn't it? Does that look like part of a frown? Over here, does that look like part of a smile? That makes it an inflection point. Yeah. If you don't see it, don't worry about it. But this is like half a frown, half a smile. An inflection point is a point where a graph changes from frowning to smiling or vice versa. And then let me go back over here and a few problems and we'll be done. So you're going to one more time sketch the graph of x cubed. And actually, I'm going to go with a little bit thicker there to make my points. So, very important 3 points. All right. Okay, that's terrible. That is a terrible, terrible graph. I'm going to try and plot that point also to make it go better. As you can see with my struggles, I understand that you're not going to graph perfectly. Just do your best. Try, please. Okay. What happens to a graph when I multiply it by 2? It vertically stretches it, and all the y's are multiplied by 2. So I want to see you take these 3 points specifically and multiply the y coordinates by 2. So I have y coordinate -1 multiplied by 2 will become -2. But it will keep the x it's located at. Over here, we have the point 1, 1. So I'm going to put my pen there, and I'm going to say, all right, multiply the y value of 1 by 2. Boom, keep that x. Now, if the y value is 0 multiplied by 2, it will stay there. And so if you can picture the stretching going on by seeing how these 2 points are being pulled apart, it is still flat in the middle, but it is twice as steep. And it's not going to draw pretty, as you can see. Then I still have the 2 times right here. So let me make sure you see this. 2x cubed, 2 times x cubed as a parent function. Okay, it's all right. Then you are taking the graph that we just drew, and you are moving it how? Tell me in chat how you are moving it. There we go. Left 3, up 1. So I'm going to first just kind of gently put in the points, the 3 points that I have in my previous graph. Then I'm going to take each point and go left 3, up 1. 1, 2, 3, up 1. 1, 2, 3, up 1. 1, 2, 3, up 1. And do you see that they have that same relationship? And then do your best in drawing, but as you can see, it is not that easy to draw it to look how it should. And I should show you the answers because that was just awful. There you go. That's what it looks like if you let a computer graph it. Okay, that's it with classwork. I am going to stop the screen